In everyday life, when you say a car is accelerating, what do you mean? I think you mean that the speed is increasing. You're not going at a constant speed of 55 miles per hour, for example, but you're pushing down on the gas pedal more and more so that your speed increases. In the English use of the word, acceleration is a rate of change of speed. When we say the car is accelerating, we mean that our speed is increasing, and when we say the car is decelerating, we mean that our speed is decreasing. Now, you could be accelerating a lot or a little. The amount of acceleration is how fast the speed is increasing. The amount of deceleration is how fast the speed is decreasing. Do you see that we're talking about a rate of change of a rate of change? Speed is a rate of change of location, and acceleration is a rate of change of speed. So acceleration is a rate of change of a rate of change. Now that's what we mean in English. Let's talk about our everyday life when we use the words in English. Let's think about the mathematics. Let's think about what's the same and different in the mathematics. First, let's make sure we understand the difference in speed and velocity. For example, recall that if the velocity is negative 55 miles per hour, that just means you're driving at a speed of 55 miles per hour, but you're traveling in the negative direction. In other words, the mile markers or the foot markers on the CBR are decreasing instead of increasing. The mathematical meaning of acceleration is the rate of change of velocity. In English, we're talking about rate of change of speed in everyday uses. But the mathematical meaning of acceleration is the rate of change of velocity instead of speed. The mathematical meaning of velocity is the rate of change of position. So, acceleration is the rate of change of the rate of change of position. We're talking about a rate of change of a rate of change. So again, position, we write that as S of t. Remember, S of t is not speed, it's position. Again, the context of this whole discussion is like the first of the semester when we were talking about walking in front of the CBR. The context is motion along a line. Could be car driving along a straight flat road. Could be you dropping a ball from a height. The motion would be on a vertical line. You could be walking in front of the CBR. Position is S of t. Velocity is V of t. Acceleration A of t. But now velocity is the rate of change of position. So it's the first derivative, the derivative of position. But acceleration is the rate of change of velocity. So it's the derivative of velocity. But velocity is the derivative of position. So we're talking about replacing velocity here with s prime of t, but then we're taking the derivative of that. So the way we write that is s double prime of t. Hence, we have the idea of a second derivative. A derivative is a function. Its value is the rate of change of our original function, but we could be talking about the rate of change of the derivative, which would be the second derivative function. Now let's look at these three position functions for motion along a line and compare and contrast them. In this first case, the position is increasing. We're walking away from the CBR. But the speed is constant because the slope is constant. There's no acceleration at all. Our speed is not increasing, our speed is not decreasing. That's what's happening when you've got a linear position function where the slope is positive. In this second case, our position is increasing also. In other words, for all three of these graphs, in every case, the position is increasing because the graph is getting higher from left to right. But in the first case, with the linear position function, while the speed is constant, in this second case, the speed is increasing also. Because notice the tangent lines are getting steeper and steeper. The tangent line right here at this point is steeper than the tangent line at this point. The tangent line here has a greater slope than the tangent line at this point. Tangent line at point A is steeper, has a greater slope than tangent line at point B. So since the speed is increasing, and this case the velocity is increasing also, because technically acceleration is a rate of change of velocity, the acceleration is positive. There is an acceleration, and it's positive because the speed is increasing. In this third case, the speed is decreasing. Notice the slope of the tangent line at A is greater than the slope of the tangent line at B. The slope of the tangent line at B is less than the slope of the tangent line at A. So if you go from left to right, the velocity is decreasing. It's also true that the speed is decreasing. You know, speed is what we think about in English, velocity is what we think about in math. I'm trying to get us to think about both of these at the same time, because the English helps us with the math. The everyday life helps us with the math. In fact, in all three of these graphs, I'm giving you graphs where velocity is positive. So velocity and speed are the same thing. So you could use them for these illustrations interchangeably. But since the speed is decreasing, we're decelerating. Think about being in the car. Our speed is decreasing. We're decelerating. So the acceleration has a value, but it's negative.